We're going to look at the paper more or less like sentence by sentence, starting from the beginning. And I'm going to try to unpack the like context and references as much as I can as we go. So the first sentence says this document is an informal summary on the FRI Low Degree Test and deep algebraic linking. And it lists some references. And I just want to talk a little bit at the beginning about what are these references. So the three references that it mentions here are the FRI paper, the deep-fri paper, and the proximity gaps paper. And I'll also throw into the list for discussion the Stark paper. And I think the academic literature of our protocol is pretty completely described. Well, that's not true. There's some Planck and Plookup stuff that's separate, I guess. But within the Stark and FRI part, like these four papers are the bulk of it. So let me unpack a little bit of how these four papers are connected and then continue. So the Stark paper is really like, that's what we're doing. We have a Stark. It's a scalable, transparent argument of knowledge is what the seal on our receipt is, very literally a Stark. So a Stark is a way of proving computational integrity, meaning a Stark is a way of convincing a third party that the computation you ran is actually the computation that you said you ran. The first part is an algebraic linking protocol. And the second part is a Reed-Solomon proximity testing protocol. And I'm just going to leave those as black boxes. I'm not going to talk about what an algebraic linking protocol is at all today. We'll talk a little bit about the idea of a Reed-Solomon proximity testing protocol, because that's what FRI really is. But for the purposes of this slide, I just want to contextualize that a Stark has two parts, algebraic linking, and then Reed-Solomon proximity testing. And specifically, the algebraic linking part turns our assertion of computational integrity into a Reed-Solomon assertion, and then the second part proves that Reed-Solomon assertion. So a lot of black boxes here, but hopefully the sort of breakdown of a Stark consists of two parts, algebraic linking and Reed-Solomon proximity testing, feels relatively okay. Each of those has two versions. There's a regular version and a deep version. We have our algebraic linking without deep, and we have our algebraic linking with deep. We could do either of those. And we have a Reed-Solomon without deep, that's FRI, or a Reed-Solomon proximity testing protocol with deep, that's deep-fri. So this is our first couple minutes of the presentation. A lot of technical words. Questions at this point? Of course, there's the question of what is algebraic linking and what is deep, but I'm going to assume, because I haven't heard any voices or hands, that I can continue. I had a little note here about like, I could be a little bit more technical. I'm not going to talk about algebraic intermediate representation too much, but there's a little note. So I mentioned that there's these two different versions. There's the without deep version and the with deep version. Deep stands for degree extension for the elimination of pretenders. When Starks were originally created, there was no deep yet. It was Ali and FRI. And then a year or two later, this deep technique was created. And at that point, people were running Starks using deep Ali and deep FRI. And then a little bit later, the proximity gaps paper showed that, in fact, deep is not actually an improvement over the original FRI. So where we are today is that when we run Starks, we use the deep version of the algebraic linking protocol, but we don't bother with deep on the FRI protocol. So that's the kind of context of the timeline of how Starks have evolved over time. There was the original, then the deep improvement, and then the realization that the deep improvement only actually applies to the first part of the protocol.
Quick question.
Yeah.
When you say FRI is actually better than deep-fri, does that relate to the execution time or execution time relative to security?
Great question. So deep is computationally more intense than not deep. So there's a little bit of extra computational burden in order to do deep. And the thought was that by doing that extra computation, you get better security. And the realization in the proximity gaps paper was that the original FRI protocol actually had better security than originally proven. And the improved FRI security achieves the deep FRI security without the need for the extra computation of the deep part. Does that answer your question?
Yep, great, thanks.
So let's just continue. The second sentence, I'll read it out loud. Based on its most recent soundness analysis, we discuss parameter settings for practical security levels, how FRI is turned into a polynomial commitment scheme, and the soundness of deep sampling in the list decoding regime. That's a lot of technical jargon. Soundness analysis is a term that you may or may not be familiar with. Parameter settings for practical security levels is sort of ambiguous. Polynomial commitment scheme is new jargon to most people, probably. Soundness of deep sampling in the list decoding regime seems like a bunch of Greek. Let's see if we can make sense of what some of these terms are. So soundness is something that I've been thinking about quite a lot recently. Suppose you get a receipt from some third party that ran our zk-VM, and you run the verifier, and the verifier says, yep, the receipt checks out, everything's cool. We don't get 100% guarantee that the person who ran the zk-VM and generated this receipt was actually honest. We don't, in zero-knowledge proofs and these sorts of cryptographic arguments, we don't get a full 100% guarantee. Rather, we get up to some probability bound, up to some epsilon, which we hope is small. We can trust that the prover knows an execution trace that actually satisfies the constraints. So soundness is the analysis associated with this epsilon. Epsilon is referred to as the soundness error, and what we mean when we say we have 100 bits of security or 128 bits of security is that this epsilon is really small. The epsilon, 100 bits of security means that the soundness error is less than 1/2 to the 100th, and 128 bits of security means the soundness error is less than 1/2 to the 128th. So in this bunch of jargon, the soundness analysis is the question of how small is epsilon. And this discussion of setting parameters is what do we need to do in order to make that epsilon small? Questions about soundness? Okay. So then there's this term of a polynomial commitment scheme is the next one that comes up. And I want to just discuss what is a commitment scheme and then add in the polynomial part. So commitment schemes, like if I'm playing, say, a guessing game with a bunch of children, and I say, I'm thinking of a number between 1 and 100, and the kids start guessing, a kid might ask the question like, wait, did you actually even pick a number? Maybe you're just cheating. And so like the simplest possible commitment scheme that I can think of would be, before we start this game, I could just write down my number on a piece of paper. And then at the end, in order to like convince you that I wasn't cheating, I could show you the piece of paper. So by writing it down on a piece of paper, I've made a binding commitment to my answer, and then I can't change it after the fact. So the two kind of keywords that come up around commitment schemes are binding and hiding. There's probably more. I didn't actually look at any references. I was putting together these slides. I just sort of like, I mean, looked at some references, but this is based on my current understanding of these terms and not based on a specific reference from a specific text. So loosely speaking, a commitment scheme consists of a way to commit, a way to reveal, and a way to check that that reveal actually aligned with the commitment. So we use Merkle trees. We commit by constructing a Merkle tree. The root is the commitment. The reveal is we show the contents of a leaf. And the verifier is able to check that the leaf contents match up with the root by checking the validity of the Merkle branch. So our commitment scheme is based on Merkle trees, and a polynomial commitment scheme is just a commitment scheme where the data that you're committing is evaluations of a polynomial. So in the example I gave in the class, like the kids guessing a number thing, I was just writing down a single number. But if I was actually thinking of a polynomial, and the thing that I wrote down was the polynomial evaluated at each point of my domain that I was interested in, then I'm now looking at a polynomial commitment scheme instead. So the way that our commitment schemes work with Merkle trees is each leaf corresponds to some evaluation point, and the contents of that leaf are the evaluation of the polynomial at that point. Questions? This is maybe up there with the most technical, like, few sentences in the presentation. Okay, I'll continue. So we discussed what a polynomial commitment scheme is. It's just how do we commit and reveal data within our proof system. And then there's this part of this last phrase has a lot of terms in it. Soundness of deep sampling in the list decoding regime. Let's unpack this term of list decoding regime a little bit. And we'll look at this in a more concrete example in a few minutes, but just for the sake of getting through the abstract, Reed-Solomon proximity testing is about how close there's these code words, and we're looking at something that may or may not be a code word, and we ask the question, is this a code word or is it close to a code word? And sometimes when we ask the question, what's the closest code word, there's a unique answer. There's like, oh yeah, that one's the closest. But other times I might be looking at some or I might be looking at some potential code word and ask what's the closest, and I might find, oh, there's like 4 or 5 that are actually equidistant, in which case I can't decode to a specific one. I can only decode to, like, I don't know, the closest one is one of these 5. And it turns out that the analysis of sorry, go ahead.
Can you just go, like, I'm not sure I understand the meaning of code, like code word.
I have a like more explicit example here in a few slides. Let me put a pin in that question, and if it's still confusing in a few slides. Now, let me just sort of invite the idea that unique decoding is where things go as you would hope, and list decoding is, oh, things are a little bit more complicated here. So going back to the phrasing, will it click? Will I go to the next slide? So it says soundness of deep sampling in the list decoding regime. For the purposes of this moment, let me just say that last part is soundness of deep Ali in the hairy part of the analysis. So here's the first 2 sentences of the abstract, which we've discussed a little bit, of a pin in Ash's great question about what do you mean by code and code word. The last sentence of the abstract, and then we'll dive into a more example of a code. We illustrate the deep method applied to proving satisfiability of algebraic intermediate representations, and prove a soundness error bound, which slightly improves on the one in the ETH Stark documentation. So in more intuitive words, we walk through a Stark using deep Ali and FRI to prove an assertion of computational integrity. We show that our security, Orbis's security, is slightly better than ETH Stark security, at least needs to do less queries, I guess, is the result there. Let me speed through this a little bit, because I do want to get to the like Reed-Solomon code part of this is really the meat here. Okay, we're in good shape on time. Sorry, I popped out to check time. So we got through the abstract, more or less. Here's the first sentence of the paper itself, which is scary. It's less scary if you take away most of the scary words and symbols, but it's still kind of scary. Fast Reed-Solomon code, interactive Oracle proof of proximity is the acronym. So let's unpack this acronym a little bit, and we'll get to what we mean by Reed-Solomon codes. So the term fast here is, there's this algorithm called the fast Fourier transform that if you're aware of, great, and if you're not, great. The term fast here is just a reference to the similarity between the FRI protocol and the FFT algorithm. Reed-Solomon codes, which we'll look at codes a little bit more explicitly in a moment, are a way of adding redundancy for the purposes of error detection and error correction. The word interactive here refers to sending messages back and forth between a prover and a verifier, although in reality, these interactions are simulated. So we run a non-interactive Oracle proof or a non-interactive argument. The term Oracle refers to a like mathematical idealized version of a hash function, more or less. So when you're reading the math papers, it will refer to Oracle proofs. When you're reading the security analysis of a real-life protocol, the word Oracle proof will get replaced with an argument. So if it is happening in terms of abstract ideal hash functions, it's an Oracle proof. If it's happening in real life, it's an argument. And then finally, this word proximity is about closeness. There is this notion of closeness within this world of codes that I have yet to really explain. And within this world of codes, we get to ask about closeness. So it's a proof of closeness. So let's get to Ash's question of what do we mean by a code and a code word. And so Mary Wooters, who's a professor at Stanford, has a fantastic course on algebraic coding theory. And if you want to dive deeper into learning about Reed-Solomon codes and the associated bounds and those topics, I highly recommend this course. There's a YouTube channel, there's problem sets, there's lecture notes. It's great. I chose a few choice slides from that in order to give a brief introduction to what we mean by a code. So stepping away from like the specifics of Starks and proofs of computational integrity and all that, the basic problem in coding theory, Alice has some message that Alice wants to send to Bob, and Alice encodes this message. So the message here is short, and it's encoded into some longer code word. But then before Bob actually receives the message, maybe there's some sort of signal noise that distorts some of the data. Maybe some entries get deleted. But so Bob's looking at this code word, or Bob's looking at this thing that was received from Alice and is wondering, what was Alice trying to say, is the basic problem of coding theory. So here's that in a diagram. Alice is thinking of some string of zeros and ones. Alice encodes the message. Alice sends it with some potential noise, and Bob receives it and wonders about what was that original message. So here's a formal definition. A code is basically, it's just a collection of code words of a specific length using a specific alphabet. So there's an example at the bottom. The code consists of these 3 words that are each 10 letters using the standard Roman alphabet, all capital letters. Let's look at another example here, and we can get a little bit more concrete about what we mean by distance, what we mean by decoding here. So here's an example of a code. It consists of strings of length 4, where every entry in the string is either a 0 or a 1. And let's imagine that Bob, oh, sorry, before we, I'm going to skip that slide, actually. Let's imagine that Bob received this message from Alice. Bob received this string and looks at it and says, oh, there was an error here, or there was an erasure here. I can't see the second bit. Bob is able to look at this, and because Bob knows the code, or Bob knows the contents, Bob knows these 8 valid code words, Bob can look at this and say, oh yeah, I can figure out what that missing bit was. That missing bit, well, if it was a 0, then it wouldn't have been in the list. So the missing bit must have been a 1. Does that track? So in this case, if I have a missing bit, I'm able to fix it. But in this case, Bob receives 0001 and looks at the code and says, I have no idea what Alice was trying to say. This was not one of the messages that is sort of allowed. This isn't something that if Alice ran the encoding procedure that she said she was going to run, she would have gotten one of these things on this list, and what I received wasn't on this list. So you can look and say, maybe Alice was trying to send, and in fact, there's 4 possible candidates here. Maybe the 4 likely candidates here. And what I mean by that is there's 4 entries on this list that differ in exactly 1 position. The first entry differs, like 0000 differs in only the last bit. And I won't go through like finding all 4 of those, but we can detect that there's an error here. But if we try to actually decode this, we end up with a list of 4 closest candidates. So what I mean by closest, I'll go back to that slide that I fixed. The distance in this context is just the number of entries that differ. And if we're looking at something that's not valid, we can try to decode it by asking, what's the closest valid one? So sometimes when we ask what's the closest valid one, we get a unique answer, but oftentimes instead we get a list. So maybe I should invite Ash. Does this sort of give a little bit of clarity to what we mean by code now? Are you still feeling confused?
Yeah, I guess I'm still not clear on like why we're measuring closeness. Like if it's wrong, it's wrong, no?
Yeah, good question. So the verifier receives this seal and has to sort of check what's going on here. And the verifiers, the amount of time that the verifier, we need the verifier to run incredibly quickly. In fact, we need the verifier to be able to run in less time than it takes to read the contents of the original computation. So that statement of like, if it's wrong, is a really, I love that question. The verifier doesn't have enough time to actually test whether it's 100% right. The verifier only has enough time to test proximity. And so we need to sort of understand, like, what's the best we can do with a really limited amount of time. If we're only allowed to read, say, like 10% of the original computation, is that enough time for us to determine its validity? And so that's a bit of a hand-wavy, loose answer, but the rough answer to your question is the verifier doesn't have enough time to tell whether something is 100% valid. And so we need to use a test of proximity rather than a perfect test. That's the best I can answer for now. I don't know if anybody else wants to add to that. So here's that first sentence. Fast Reed-Solomon code, interactive Oracle proof of proximity. I'm not going to talk about this definition, but I figured I would include it for those who are interested. This is a formal definition of what a Reed-Solomon code is. It's, again, drawn from that same course on algebraic coding theory, which I highly recommend. For the sake of making this like a reasonably accessible to everyone discussion, I'm going to avoid, like, Reed-Solomon, discussing Reed-Solomon codes involves finite fields and polynomials in a way that I think we need to do a sort of primer on polynomials and finite fields before I want to have a study club that goes into the details of Reed-Solomon codes. In a very loose way, Reed-Solomon codes are codes that are based on low-degree polynomials. So what do we mean by this low-degree test? It elaborates. It says, FRI is a low-degree test for functions on an FFT domain, i.e. a smooth multiplicative subgroup D of finite field F. This is sentence 1. Again, if you don't have a degree in math, reading this is probably pretty tricky, but maybe it's easier if I take away some of the harder words. What FRI does, given a function called f, FRI proves that f corresponds to a polynomial of low degree. And this word corresponds means is close to rather than is exactly the same as. Bringing in a little bit more language, we have, it's not just low degree, it's low degree with respect to the size of D. And there's this function notation that you may or may not be familiar with. So what's the function notation? What's D and what's F? This notation says that we're associating each element of D with an element of F. So D is a set, F is a set. Given any point in D, we can evaluate the function F with that point as an input. And the output, when we evaluate it, will be an element of F. D is our initial commitment domain. This is the size of our Merkle tree. We construct one Merkle leaf for each element of D. And F is where we do our arithmetic. So it was Baby Bear, it's going to be Goldilocks. I guess it's going to be field agnostic. Adding in a little bit more of that language. Now this is actually the beginning of the paper. An FFT domain, again, not going to get into this too much, but it's a domain where you can do finite Fourier transforms. More or less, it means you can split it into smaller pieces over and over and over again. And not going to get into the definitions of those terms. Questions at this point? I want to sort of step back and try to invite a little bit of discussion if it's possible.
Can I add a little comment?
Yeah, absolutely. Yeah. Question. Yeah. That
Proving that you correspond to a low degree polynomial is related to what a Reed-Solomon code is. Paul didn't go into, for good reason, what one is, but that's a relevant measure of closeness. So just sort of wanted to mention that as to help people connect the dots.
Yeah, I appreciate that, Tim.
I feel like a dum-dum still, but I don't, why is close good enough? Like, don't we want everything to be correct?
Great question. There's this idea of redundancy in error correction contexts. And what Reed-Solomon codes are doing for us is making it so that if there's any error at all before we do the Reed-Solomon part, then the Reed-Solomon part is going to drastically amplify that error in such a way that it's very easy to find it. So if there was one discrepancy originally, after we do Reed-Solomon encoding, 75% of the thing is fucked up. And then we tested a little bit, and we tested enough that we are confident that we would find it because most of it would be in error. So there's a 3 Blue 1 Brown video about Hamming codes that I think might be the best source of getting an intuition here for why closeness is enough for us. But this term proximity gaps is actually related here. A proximity gap refers to the idea that if it's not, how do I explain what a proximity gap is? There's nothing that's only kind of close is the nature of a proximity gap. So essentially, once you do the Reed-Solomon error amplification process, either things are going to be pretty far or correct. And so by running the test says that it's within the pretty close area, and because of the proximity gap, we get to sort of conclude that that's enough. So you're not a dum-dum for having this question of why close is good enough. It's actually like a very, very, very good question. And
sorry, Paul, I also have a question related to this closeness that you were mentioning. Is it somewhat related or similar to the Schwarz-Zippel lemma?
So the closeness,
right?
It doesn't feel super closely linked to me there. The Schwarz-Zippel lemma, for those who aren't aware, essentially says polynomials don't have that many roots, and so if you're looking at polynomial stuff, you can bound things based on the number of roots. And the distance here is really just looking at how many entries disagree. So I don't know, Bolton, do you want to comment at all about that? Do those feel linked to you?
Yeah, I sort of agree. I think that, the Schwarz-Zippel lemma is, maybe a generalization to sort of multivariable polynomials of the sort of, as you were saying, Paul, the sort of very simple fact that if I have a polynomial that is low degree, it only has a certain number of roots, which is basically the same thing as saying that the polynomial is only going to be equal to zero in a very sort of small number of places. And what that tells us is that if you take a polynomial and you inspect it at a bunch of random places and you keep seeing that the polynomial is equal to zero in those places, you can be pretty sure that the polynomial itself is actually equal to zero. the full sort of general Schwartz-Zippel lemma does come up in some of this more complicated analysis, but I think for the purposes of this talk, it's probably better to just think about it, the simpler fact that polynomials tend to be only equal to 0 in a lot of places if the polynomials themselves are equal to 0 everywhere.
In some ways, the Schwartz-Zippel lemma gives an intuition for why you can be close to just one code, where if these Reed-Solomon codes are low-degree polynomials in some sense, that the fact that there are only a few roots is some intuition for why, if you have some random thing that seems kind of like a polynomial, it probably is that polynomial-ish, kind of. But like, probably only one. May I don't know how we're doing on time, but can I
Go ahead.
add one comment on the on Ash's thing about good question on like, well, why is close good enough? Which is in some ways how we do the code to run the verification and how the proof is framed are in some ways backwards of each other. If you're running the verification and you see a single thing wrong, it fails. It's bad. There's a problem. You're like certain there's a problem. It's bad news. The proof is saying, hey, look, how much can we try doing stuff and still getting okay results until we've gotten close enough that we can be extremely confident that there isn't some problem hiding away from us. So close is sort of us getting close to the actual answer without looking at it, rather than being like, oh, well, if it mostly passes, it's good enough. Like, no, it's not that if it's mostly passes, it's good enough. It's that you don't have to check the entire world.
Yeah, that's a good point, Tim.
I'm wondering, is this related to the zero knowledge portion? Like, we add noise, right, to kind of mix things up so that it's hard for people to, recover the execution trace, to recover the actual computation. So I guess my question is, if there was no zero knowledge, if it was just computational integrity, would there be a closeness? Is closeness related to the noise we add, that mixing it up and everything?
Not that, I don't believe so. I think that regardless of even if we wanted to do a non-zero knowledge implementation of this, I think it would still have the exact same closeness and proximity discussions.
So it enables it to be zero knowledge, but for efficiency reasons. So if you actually check the entire polynomial, you can't really do zero knowledge. That breaks zero knowledge. So it is related to zero knowledge in that way. But you would still, for efficiency reasons, to make the verifier run fast, even if you aren't trying to do zero knowledge, you would prefer not to check everything. So in that way, you would still not check everything, even in a non-zero knowledge case.
Yeah, Frank, I can maybe be a little bit more explicit on the do I want to actually? Essentially, the verifier gets some information in the context of this test, and we add information, we add the random padding in order to make it so that they can't do anything with the information that they receive. That's not as explicit as I was thinking I was going to make it, but it's as explicit as I'm going to make it for now. We can talk more about that after if you want to, Frank.
Sounds good. Thank you.
I do have a few more slides that I could run through, but I think it might be more valuable to like invite people to vocalize what they're either confused about, curious about, interested in. I'm thinking that I will facilitate some sort of introduction to finite fields over the next few weeks, and then maybe another one of these that goes a little bit more into Reed-Solomon codes, assuming some finite field background. But for today, I'm curious what's on people's minds about either things that are feeling like a barrier for you in your current understanding, things that felt confusing to you about what we've talked about so far today.
Just have a short observation. So I think,
Yeah.
at least, my opinion, so far this has been one of the most exciting work-related calls I ever had.
Thank you. That's
It
cool.
is really good. Paul, I would love to learn more math from you. You're really good at this.
I appreciate that. Thanks. It's something I'm pretty passionate about. So I mean, I'm happy to run through the last like 10 slides that I have prepared if people don't have things that they want to vocalize. Okay, I will just go ahead and go back to my thing and wrap things up a little bit. So the next paragraph is just as scary as the previous one. I'll read it out loud. The oracles, that's idealized hash function sort of thing, kind of provided by the FRI prover are again, oh, actually, the way I'm using oracles is slightly wrong. Well, it's good enough. The oracles provided by the FRI prover are again functions on D or a subdomain of it, and the verifier queries the values at points from their domain only. Due to the small size of D, the key tool for distinguishing one polynomial for another is statistical sampling. However, a statistical test can only assure proximity, which we measure by the fractional Hamming distance. So again, don't panic. I'll take away some of the complicated stuff. And this gets back to Ash's question of like, why is, well, it gets kind of back to the question, Ash's question of why is closeness good enough? What we're doing here is we're doing a statistical test, meaning we're choosing some random points and we're saying, did it pass there? We're doing some random tests and we're saying, did it pass the test there? And this, by the nature of this sort of test, unless we test everywhere, all we can really get out of this is proximity. So yeah, if we want the verifier to be able to run in any sort of efficient amount of time, we have to find a way to make a proximity test be good enough. And it turns out that Eli Ben-Sasson et al. Have done that for us. So to sort of boil it down, FRI gives us the tools to test, is the code word I received close enough for me to decode? And with a few dozen queries, I think in our protocol, we're doing 50 something right now, we can determine if the code word is in the list decoding radius, meaning there's a few viable closest code words. This was our example that we saw earlier of a list decoding sort of situation. And with more queries, we can determine if it's in the unique decoding radius. We can actually find one code word that it corresponds to.